We're going to talk about graphing data. So we've already in a previous video examined pictographs and bar graphs, but I want to point out a few key features here. They can be arranged either vertically or horizontally. We can have our pictures in our pictographs each represent one object. These are each one bead, or in this case, one little person here represents 1 million people. So we can set a key that tells us that one picture is worth more than one. We should on any pictograph be able to overlay a grid such that every picture falls in one cell. So we want to have them take up the same height here so we don't get thrown off in our interpretation. Here each person is the same size, they weren't drawn differently, and they fit into the cells of a grid. On the bar graph, what I want to point out is that the scale should be consistent across the whole axis. So here one space represents 2, the second space represents 2, and so on. We don't want to have, another space represent some value other than 2. So let's look at that in terms of mistakes. Here is a messy pictograph, and we can see where problems come in. So usually we assume that the tallest column represents the greatest category here. The banana column is tallest. So in this, and this is something about food sold, I think, it looks like more bananas were sold than hot meals, but actually more hot meals were sold. Down here we can see on the key, each banana represents 20, each hot meal represents 20. So there were 80 hot meals and only 40 bananas. So it's misleading how it is in there. Similarly, it seems like there were fewer hot drinks than cold drinks and such. So we could fix this by having consistently sized pictures and having them line up in a grid here. So if I had my grid, I could have my banana and I could have my hot plate be the same. It would be easier to compare. With bar graphs here, the first thing to point out is that we're labeling tick marks. We're not labeling spaces. When I labeled spaces on the other graph, I was showing the value of each space. Each space was worth 2. Here, this space isn't worth 1. This space isn't worth 2. You're marking the end of the space and counting them. Sorry about that. So let's look at this bar graph and see what's missing. No title, so we could add a title. No labels or labels put incorrectly. Let's go ahead and add some labels in here. So we can add the labels, and another thing that we notice is that one of the bars is the incorrect height. Here we have the 400, here we have the 325, here we have the 250, and so this guy should also be 250. Over here on the right, we can see the problem with these is they're actually both the same data, but by playing with the y-axis, we can interpret it differently. So people can tell any story they want with statistics usually. Fuel prices remain stable, but there's all of this empty space up here that could have been avoided if we would have had the maximum be up there at 200. And on this one, we didn't start at 0. So on a bar graph, it should be that a bar that is twice the height, and this one is more than twice the height, should be twice the value or more than twice the value. But this guy is 60 and this guy is 80. So it's really misleading because it looks like I've more than doubled in 2003 when actually I haven't. So we want to start at 0 down here and pick an appropriate scale. Another mistake here is a lot of times people will just start labeling the axis with their data, 3, 4, 5, 7, 3, 4, 5, 7 here. And again, we can see that this space is worth 3, this space is worth 1, 1, and 2. So we want to have each space be worth the same value, so that's a problem there. Over here, we've connected the dots, but you should be able on a line to pick any point on the line and make meaning from it. So what does the point mean that's between pink and purple? Here, it's hard to interpret that. So on categorical data, we don't tend to connect the dots. All right, so moving on from a bar graph to a pie chart, a reminder here that a bar graph can be really good for looking at part-to-part comparisons, or if we have time increasing to the right, bar graphs can be powerful. Whereas in pie charts, we're looking at part versus whole, so we're looking at the part here versus the whole circle. Pie charts are easy to mess up. Some of the mistakes that people make are they don't have mutually exclusive categories. So in this case, we have an example where there's a survey of the friends, they have the favorite type of movie, and then we have an appropriate pie chart here. So mutually exclusive means that every friend had to pick one movie type, so one friend did not show up in multiple categories. So they were mutually exclusive. The sum of the parts adds to a meaningful whole. If we add all of these up, we get 20, which is the number of friends that were part of the survey. So it's meaningful to compare the part to the whole, 4 out of 20 friends, like comedy, and then we can represent it. So again, this is the part-whole relationships that we're looking at. So this over here is what we were just looking at. If I change the question to not be what's your favorite, but what movie types do you like? So that means one friend could show up in multiple categories. We start to have a problem with pie charts. So if I take each number and divide it by 20, the number of friends, well, that tells me 90% of my friends like comedy. But if I were to try to put all of these on the same pie chart, it wouldn't add up to a meaningful 100%. These add up to much more than 100% there. So if I wanted to do a pie chart, I'd have to do a single category where I just looked at comedy and it was like, yes, no, do you like comedy? And I would have 90% say yes and 10% say no. So I could decide to switch up the whole, since these would definitely go more than 100%. If I add up all of my data here and get 60, I can add it up and then I can find out 9 out of 60 is 15%. But what does this represent? 9 people like sci-fi out of 60, not 60 people, because there were the 20 friends. 60, yes, I like a category. The whole doesn't make sense there. It's not meaningful. So even though you could create a pie chart, it wouldn't be a meaningful pie chart, because who knows what this whole represents. Pie chart mistakes. This is a classic one. It showed up on a news station where, again, we don't have a meaningful whole and we probably don't have mutually exclusive. Probably the survey, you could say that you'd be interested in any of these candidates, and so you could show up in more than one category. Over here, our problem is, this was a Google search for computer programming languages. The person who graphed this only put 3 on there. So notice this doesn't add up to 100% to some meaningful whole. If you did all the computer languages on there, this looks like a totally different picture. You can see that this is just a small fraction relative to all of the computer languages there. All right, moving on to dot plots. We have numbers on the axis, and each dot represents a single data point. If we have varied data, so down here, average January temperature, you can imagine looking at the 30 to 39 category. Maybe the data were 31, 32, 33, 34, 35, 36, which would give you a dot, 1 dot in each category, which would not be very interesting. So sometimes what we do is we create intervals and lump data together, put it in the same bin, and then you can start to see a more interesting pattern. Just like we could blur the pictograph into a bar graph, we can blur this into what we call a histogram. So here we have number intervals, and then we have the frequency or the count right here. So these guys are closely related. This is an interesting example of a dot plot that needed some work to happen. Our data is electricity across the world and which countries have access to electricity. So we couldn't put in a dot plot. We don't have numbers here, we have countries. So the way they've handled this is one, by rounding the numbers to the nearest 10%, and then counting how many countries were at 10%, how many countries were at 20%, and then making the dot plot percent of population with access to electricity, and each dot represents one country. The big mistake comes in, each dot is a data point. I can list out all of my data points. Each dot is a data point. Where we get mistakes, some people will interpret the height of the tower to be the data point. So if you were to list the data, you should have a whole bunch of data points, one for each dot, as opposed to one for each tower. Bar graphs and histograms look similar. What we need to look at here is that we have categories for the bar graph and number intervals right here for the histogram. Usually with histograms, we put no gaps in between the columns, and with bar graphs, we do. Our last one is a line graph. When we have continuous data, continuous meaning I could pick any number in between the numbers that I've shown. So here I have, what do I have? Average math scores of age 9 students on a long-term trend test. Here we could pick the line graphs, we connect the dots, whoops. We could pick any point and make meaning in that. So this, I would say, well, that probably was about 1988, and at that point in time, I could expect that average score right there. Notice that we don't always start line graphs down at 0. Sometimes when we have a bar graph that we're comparing and they're fairly flat, we'll do a kind of a zoom out into a line graph to show the range of interest. These are only appropriate for continuous data, not categorical. So again, here we have states, and if I connect the dots, what does it mean, this line between Washington and Oregon? I can't interpret that. So students make lots of mistakes on graphs, and getting that critical eye for what important features need to be there is key for a teacher.